So today we're going to try and understand how the buildings work, how it lives, breathes, moves, uh, allows air to go through it, how air comes into it and goes out of it. There's many different ways that things are caused, or different things that cause vapor to move through a building. The Minnesota Pollution Control Agency has requirements and different types of materials that are subsoil, whether it be old dry cleaning chemicals, oils, hydraulic fluids, those sort of things. And some of the things we're going to talk about is how those things could get into the building, how we need to be able to deal with it, and keep that from happening. We're going to try and talk about the subtle air movements that take place. You may not even notice it when it's in there. And we'll also talk about how some of the air gets into the building that you never anticipated having happen. So some of what we're dealing with are what are pressures. You know, we have all heard that buildings need to be positively pressurized, particularly in Minnesota here where we have cold winter seasons. We try and push the warm air out rather than pulling the cold air in. But you don't want to be putting so much pressure in that you're keeping the doors standing open and then that you're pumping so much air into wall systems, roof systems that you're going to cause condensation. So some of the things I'm going to lead off with here are some of these pressure discussions. So blower doors are systems that we use for testing for air leakage in the systems. The Corps of Engineers dictates a Pascal rating of 75 for those type of things. Common ductwork and ventilation systems, we have water columns of 1 to 2 inches and up to 4 inches as normal static pressure in ducts created by the mechanical system. That equates to this 250 to 500 pascals. So here's kind of a view of things. Now in the lower right you'll see that I have 3 pascals listed, and on the right hand side equivalents to that. 3 pascals is what most of the control agencies are using as the differential pressure between subsoil areas and the atmosphere within the building. As you can see, if we're talking PSI, that's down into the 4th digit past the pyramid or period, just to try and get a very, very tiny amount of pressure differential. However, you go to the left-hand side, 1 atmosphere, essentially what we're all feeling today. You look down at the bottom, and that's up in the 100,000 pascals of pressure. So the differential that we're looking and having air passage, vapor passage from beneath the floor slab up into a building is very, very minute. So here are some of the things that we have that happen in a building. We have convection. Obviously, warm air rises, cold air drops. They depend upon that for operation of fin tube radiation systems. On higher buildings, we have what's called a stack effect. High-rise buildings, I don't know if many of you have ever gone into the upper floors from a stairwell in a high-rise, but that rising air can create an excessive amount of pressure, making it very difficult sometimes to even open doors at the upper level. Mechanical ventilation is those things where we try and create that differential pressure between the inside and the outside, and static pressure is similar to that, but it's located within ductwork. So that's a little bit more pressure over what the atmosphere is within the building. Natural wind pressures, and I'll show you a graph of this, have a great effect on the building, even on the interior. The adjacent spaces, the reason I have that in there is, what if you have a building that you have constructed over the top of an old dry cleaning facility, and what you've got there is a pizza business on one end of the building and an office on the opposite end of the building. Well, what ends up happening, there's so much vacuum that's created by the pizza oven and heat rising through a stack, mechanical ventilation, that it can create an excess of negative pressure and actually pull air through wall systems or through the roofing system, through the flutes in the roof deck and so forth. Fresh air intakes. These are areas that when we feed mechanical systems, it pulls air from the outside, so we bring in fresh air and we exhaust it. However, we find in a lot of places, can be condominiums, small businesses and so forth, that people defeat these systems by either closing them or putting insulation in the ductwork or a block in the ductwork somehow, so that they're not having to heat and cool that air to reduce their air conditioning costs. Not probably the right thing to be doing. We'll talk today about some of the control systems and how it's not just temperature controlled anymore, and it's not necessarily pressure, and then buoyancy of some of these things. You can have various materials. We hear lighter than air, heavier than air, whether it's hydrogen, helium, carbon dioxide, or fumes. Most of the fumes that we're dealing with are not lighter than air. They actually hang closer to the ground. So how does mechanical ventilation or building ventilation work? The picture on the right is Westminster Palace, and this tower that's located not too far from Big Ben actually creates a negative pressure and a stack effect, and those windows that you see there through the top are operable and actually allow the air to go through. So what they're trying to do is pull in outside air, pull in fresh air to meet some of these requirements, which at the time of construction there we didn't have building code requirements, but the building codes there talk about living areas where you have 0.35 air changes per hour or 15 CFM per person. That's the requirements of what we're supposed to be bringing into a home, for example. Garages, you can see there 100 CFM per car. Parking ramps, 4 to 10 air changes an hour for commercial buildings. Hospitals are even in excess of that. You can be in the 20 air changes an hour to get out odors, germs, and provide purified air and filtered air. ASHRAE, one of the organizations that are used by the engineers in designing things, has all their alternatives for energy usage there. They're talking about 6 to 10 CFM per person in commercial areas. One of the things we look at, I've got tight houses listed there, is 0.5 to 0.41 air changes per hour. But homes, for example, depend upon fresh air coming in as leakage to the interior, oftentimes from the exterior. And you can see the difference between that. It's about double for a loosely insulated home. In building occupancy, we see all sorts of different things being used. As I mentioned earlier, higher volumes for healthcare. On the right, you'll see on the top, a through-wall unit, or sometimes called a split unit, where you've seen these in hotels and other things, maybe smaller offices. It brings in a certain amount of air. And the amount of air that's in there is a very small opening that's located inside of it. And there's usually a damper that's in there. These, again, sometimes get defeated. They get taken apart by hotels. You ever been in a hotel where you smell chlorine throughout the building? That's why. Those things only operate on a periodic basis when heat is needed, and that's the only time when it starts bringing air in. We also see in the lower right what's sometimes called a magic pack unit or a combination unit that's placed in the wall in condominiums and apartments. That has the same type of thing, a small damper in the bottom. It's often manually operated or set by the balancer originally, and these units are put in a closet. Oftentimes we're seeing problems with those that they get defeated because homeowners find cold air drifting out of there when the air conditioning, when the heating is not functioning. What ends up happening is that cold air just lies on the floor and drifts out under the door to the interior. So we have to make sure those rooms are sealed. We have to make sure that the mechanical ventilation is there and that it's all balanced, so it takes and brings in the air when toilet exhausts, kitchen exhausts, and dryers and so forth that are in condominiums are used. So here's some of the principles that we'll illustrate. The first one on the left is in old times, back in the 70s. We used to have something, we're doing energy efficiency things called a Trombe wall, T-R-O-M-B-E, I believe it is. The sun comes in, heats up those surfaces, and what it does in the lower opening brings air in. As it heats it up, it goes out through the top. Later in the presentation, I'll show you some pictures of buildings that are using that same principle, but on a whole building, not just necessarily a room area. Give you an idea how warm this space gets. We are working on a project in Chicago that's a 93-story high-rise. They have a concrete wall behind glass like this, and that space, by simulations right now, has been predicted to be about 250 degrees inside the glass. So it can be a very, very warming thing, particularly if there is no air circulation there and it continues to warm. Then air finds its way wherever it wants. On the right side, it's the same kind of thing. We ventilate air in low, it goes out high. Stairwells are often an area where air gets passed through, and we don't have a whole lot of makeup air because it's not an occupied space. So those need to be taken into consideration when you're designing the building to make sure that you've got those areas well sealed. Here is one of those examples of a solar chimney, as they call it now, which is very similar to that convection. What they're doing is using the sunlight beating down on the roof to heat that air and create a hotter environment that causes the air to go out at the top and be brought in from the bottom. Stack effect is things like stairwells, atriums. It's that pressure that resides. I've worked on a building in downtown Minneapolis. It was a 51-story IDS building, and literally to get into the mechanical room on the top floor, it's necessary to put your shoulder into the door and push on that with all might that you can, because that force coming up there and trying to get out the top of the building is so extreme. Now, obviously our air moves from higher pressure to lower pressure, so we have to look at what's the second floor like, the first floor, as well as the exterior. Some of these things, if we look at the stack effect like this, that same illustration, imagine where those small arrows are on the bottom. I'll move the cursor over here, right down on the bottom area here. Imagine that's a parking lot underneath a mixed housing project or a mixed use project. And what we want to do is we want to prevent the exhaust gases and other things from getting from that parking ramp up into the building. As you can see, it naturally wants to kind of go that way. If there's a stairwell or an entry and those doors are open, it wants to go that direction. So what we have to do is provide mechanical ventilation down there. It's often done by a heating unit on one end of the building and an exhaust fan on the other. They're actuated either by a carbon monoxide detector, a cycling of the fan just on a periodic basis, or even on a temperature basis. If you have parking under there and it's open air, now you've got atmosphere on the underside of the building as well as top, bottom, and sides. The mechanical ventilation. This moves the air throughout the building. Now it can be provided in the attic space, it can be exhaust fans. We're often bringing air in from exterior ducting. For mechanical systems, either directly to a furnace, directly to an air handler, and we're pushing that through. These pressures, we have fans that will pull air in, and believe me, it doesn't take a whole lot. We've worked on a hotel that had some mold growing on the walls between two occupant rooms. That mold is not where we would normally see it. What was happening is the air was being drawn through the weep system and the brick up underneath an incomplete air barrier system into the walls by the little toilet exhaust that took place in each of those bathrooms. We've all been there. We know that when you take a shower, it doesn't necessarily pull all the air out, but it's enough to pull in enough moisture, have the air conditioning system blowing on the wall that created mold and enough humidity or condensation there to cause mold growth. The Metrodome, which is no longer in existence here in Minneapolis, had an air system that only had this, as you can see, 0.04 to 0.4 psi, which isn't much, but when you take that over every square inch, that's a lot of force that keeps that roof up. If you ever had a rupture in that roof, you'd be able to go and plug that by just dropping a piece of plywood on the system, and the vacuum would hold that piece of plywood up against the wall system and seal it off. So what we look for in these mechanical systems is a balance, and typically at buildings we have at the completion a balancing report. It takes into account air leakage coming into the building through cracks, grooves, window perimeters, door perimeters, people operating doors. It also takes into account the amount of exhaust that goes out through exhaust fans, kitchen hoods, bath fans, dryer vents, furnaces, and so forth, and then we bring in an appropriate amount of air from the bottom or from the exterior. So if you don't have the appropriate amount of air coming in, your ventilation system will not take it out. Again, I've got there, it's trying to suck the air out of a pop bottle. It's not going to happen. You're not going to get the air out of the bottom of it. So we have to make sure we've got that balance. So if you were to look at kind of a formula, it's always exhaust plus stack effect type of things, less the exhaust fan, mechanical ventilation being brought in, air being brought in for combustion air, as well as any other air that comes in. And it's usually about a 7 or 8% fresh air that we like to see brought in through the air handler. So static pressure can be created in a bunch of different ways. Some examples here, the pressure can also occur just because of temperature differential. What we're looking for is these differential pressure, and when we're talking about inches of mercury or inches of water, you can see on the right hand side what we call a manometer. It's essentially a U-bend, and the vacuum that is present pulls up a certain height of that liquid, and that's what we measure. So we measure in inches of mercury, inches of water, column, PSI, PSF, all those sort of things. So we have wind pressure that goes against a building. Try and get an idea of how much wind pressure is affecting us. The 20 pounds per square foot is listed up on the top there. Is as little as 0.13 psi. That's not even enough to inflate the tires of your car at home. But if you start getting up into the 100-mile-an-hour range, you're starting to see pressures of about 29 pounds per square foot. You start adding those things up, and you start to figure out why why buildings move around in the wind. This is important because it pushes its way through any cracks or grooves that we have in the building to the interior. Here's an example. This is a case study of a building, a barracks building down in Fort Leonard Wood. It's 3 buildings high. We did a blower door test on this. Now this is one where the Corps of Engineers wants 25 pascals used. Now you run the building through a number of different cycles, and you test interior in several different areas, and you monitor those things. You can predict about what the air leakage is going out by the amount of flow that you're putting in, and knowing what the pressure is. Therefore you can back calculate this and know how much volume is going out through those openings. They use this 0.25 CFM per square foot as the maximum amount going on, and that's all of your surfaces, top, sides, bottom, 6 sides of the box essentially. So we went to do this test. Now what you see here is the white lines, the blue lines, and so forth. Those are the different monitors we have. Look how nice and organized those things are. They're very tight little steps, as the fans would step up the pressure inside the building in each of those cases. There's a nice calm day on the outside. Doesn't affect us a whole lot. What you're putting in is what you're getting out. However, you start to get a windy day, and you can see how those numbers are all over the place. Very, very hard to get a prediction of what's going on. That's measurements inside the building, not outside the building. So exterior wind upon our structures has a big influence on what goes on in the interior. Just so you know, when we do these tests, we go block off things like air intakes, other vents. Things that we can't get to are things like conduits that are running out for electrical, that have the annular space around the wires inside the tube, go to the exterior or outside of the environment that we're testing, and air can pass through those little bitty things, as well as, like I said earlier, the flutes in the roof deck and so forth. So adjacent spaces, we have balancing issues. What do you do if you have a swimming pool on one side of a building? We want to make sure that that's a negative pressure area, but we still want it to be positive to the outside. We don't want the chlorine gas or fumes to be floating through things. One of the big issues that we see, as I mentioned earlier, is the flutes in the steel deck. The board insulation that you put on top sits there, and there's these little flutes. They're what, about an inch wide, inch and a half high, something like that, and they extend from one area to another. Sometimes those extend into wall cavities, and they're great places for air to commute. Any place that you have a penetration or a seam in those decks can find its way through there. It's like a giant linear diffuser. Again, materials, any place it changes, we have transitions. Even in window systems, curtain walls, we have what are called air transfers or weeps that create a pressurization. And in today's world, we're doing things called rain screens on the exterior. The building codes are now requiring a continuous insulation on the outside and a continuous weather barrier on the exterior of the building. When we do that, often the insulation is placed outboard of the weather barrier behind some kind of a finish. It could be a brick exterior with 2 inches of foam in there, and then a weather barrier and the studs or steel framing or whatever it might be on the inside. Could be concrete block. Or we have these systems now that are essentially an aluminum panel. Could be a ceramic panel. It could be tile. It could be all sorts of things. And those are mounted to an aluminum structure or framework with small gaps between it. And what they're doing is depressurizing the skin of the building so that any air that comes pushing against it doesn't push into the building, doesn't change the temperature in that insulation, and makes it effective. So all these things are occurring, but we have to have much better, tighter weather barriers on the outside. As you can see there at the bottom, I put air barrier installation. Air barriers are supposed to be continuous and airtight. They need to be structurally sound. You can put a layer of plastic up around things, but if you're just attaching it to the studs, what's going to keep this pressurization when we run 25 pascals of air against it over a large area and keep it from tearing off of the wall? These air barriers are not necessarily always the weather barrier or the vapor retarder. All of those things have to be considered in the wall. So here's what we're talking about with fresh air intakes. Systems are designed to bring in that 6 to 10% fresh air I was telling you, or that normal occupancy. Numbers like 7% always kind of stick in my head for that fresh air. If you are using a fin tube radiation system and you have vapor intrusion potential coming from underneath the building, how are you going to supply some kind of fresh air to be able to take that fumes out and exhaust it? Well, you haven't got it with a fin tube system, so you have to have some kind of supplemental makeup air system. So you'll have two different things going on there. The PTAC units or magic packs, or those split units that we showed you a picture of earlier, bring in that small amount of fresh air, but that has to be balanced, as we said. There's the formula for the pressurization. The air supply less the air loss equals your return air that we're bringing back, and the fresh air, that 7% that we're adding to it. Those two numbers have to balance or to be slightly positive. I have been in condominiums and apartments before. That's a famous area for the associations to try and save some money. So what they do is they go shut that unit off. Then there's no ventilation. So on the third story of a building, we've read high levels of carbon monoxide and high levels of carbon dioxide. One of the indicators that you have for how much fresh air is going around in the building is determining how much carbon dioxide you have. If you got a bunch of people and we're all breathing, we're generating carbon dioxide, and you can measure that. And it's down in the 600 parts per million range that we want to make sure we don't exceed. If you start getting into 1,200 parts per million, take about 4 or 5 points off your SAT scores, because your brain is going to be thinking as well. Building control systems. We have some of these things that are working against one another. One, we're trying to keep fumes out of a building, either by the materials we're putting in, which is what LEED looks at quite heavily. We're trying to keep anything that's subsoil nature from coming in. And we're trying to keep the buildings as energy efficient as possible. So if I'm bringing in all sorts of fresh air to keep myself happy and keep my carbon dioxide levels down, how do you then take and deal with it when everybody goes away? There's one building we've looked at that had a difficult time. They were using a much higher level of energy than what they expected the building to be designed for. It was a LEED Platinum building, and after a year of occupying it, people were rather concerned because their energy bills were not better than what they were thought they should be. And what happened is this occupied versus unoccupied mode. The computer system, and we have computers that control all of this stuff nowadays, were set in occupied mode all the time, which constantly brought in fresh air. If you don't have anybody in the building, no reason to bring in the fresh air. So they were heating up 6 to 10% of the air coming in 24 hours a day. This was a big energy hog. They fixed that and things got corrected. CO2 sensors are another way that some of the LEED things, like large classrooms, office areas, when you start getting carbon dioxide levels up in that 600 parts per million, it turns on the ventilation system and starts to ventilate things. Once you've got fresh air and you brought it down to a certain level, it will shut off the ventilation and continue to recycle the air in there until it needs to be boosted back up. We've got other things like, return air exchange systems. So when we have those, or heat wheels, we're bringing air in from the outside. We're trying to heat it with the inside air. So you can kind of get some free heating from those things, but again, that works on a pressure differential from the inside to the outside. The breathable buildings, as we showed on the first page, that's an actively working building that monitors the temperature, the humidity, carbon monoxide, carbon dioxide, and opens up those vents on a basis allowing things to change and get better. So the buoyancy, not really much of an issue when we're dealing with vapor intrusion in the types of buildings we have, because most of this stuff hangs relatively low. So you have to really know what kind of chemicals that you're dealing with, and the chemicals are also very important in the selection of what we use for a vapor retarder under the floor slabs, as well as on the walls. So we'll talk about that for a little bit. So think of the vapor retarder that we place underneath the floor slab as a coffee filter. What we're trying to do is we're trying to make the molecules stay outside. So how do we do that? We've all gotten some Gore-Tex stuff that we wear. The moisture vapor is supposed to go out. Why is that? Because moisture vapor is 2 molecules in size. And you can kind of see on the right-hand side, that's what a moisture molecule, water molecule looks like. However, if you start getting it into a liquid state, it's 90 molecules chained together. That's why water pours as a stream rather than breaking off in pieces, because it's kind of is a longer molecule. So what we look for is what size is the material that you're trying to filter out. So you've got angstrom sizes, different types of things. People can look this up and you can talk with the manufacturers. And a lot of the things that we've used are things like Raven or Stego as a vapor retarder underneath there to stop that stuff going through. And we call up the technical service people and say, I've got this kind of a object. Most of them are testing vapor permeance, the ability of water vapor to go through these membranes. So again, if you've got a molecule that's larger than water vapor, and you can see that's what 1.515 angstroms in the upper right corner there. If you have something that's bigger than that, it should be filtered out by the membrane. So that selection is really important. The durability is really important as well. That's why most of the time we're looking at things being 10 mils thick to try and gather that material up. All right, so here's some of the different types of things that are going on. You can see the different sizes of the molecules. When you start getting into your hydrocarbons and so forth, which is your oils, gasolines, cleaning chemicals, they're a much larger molecule, stringy in nature, sometimes more spider-like. So you can see here's phenols and ethanol and so forth. It shows how complex those elements are. So vapor mitigation systems use not only the vapor membrane on top of the soils just underneath the floor, they also utilize a negative pressure zone underneath. So we put in a coarse gravel, aggregate, sand, and place a vent down into that can either be passively vented by air passing over the stack on the exterior or by placing a fan on there. And again, normal systems has been used is about 3 pascals in differential between above and below. So how do we measure it? We drill a hole in the floor and you insert a probe, you seal it down there, and you measure with a manometer above and below. It's pretty simple. Some of the membranes that we look at aren't necessarily as solid as they would seem. Concrete block is very porous. In fires, you can actually have smoke go through concrete block. So any passage of air through that is going to be just about the same for any kind of vapor that you're trying to resist, hydrocarbon vapors and so forth. Also, one of the things you have to be concerned with in designing these buildings is you've got a foundation that goes down and the concrete block is hollow. Can the hydrocarbon vapors that we're talking about enter into that cavity in the concrete block, transfer up through those things up above grade? Think of a house that's kind of got a partial walkout on the back and is tapered down on the sides, and you have those little knee walls along the sides that go from the front of the house to the back of the house in the basement. Most people put a little shelf on there, put their knickknacks on it. Well, actually, that's bringing air from the bottom down by the footing all the way up into the top of the house on that little shelf. So those areas need to be sealed off as well. So either you can do it under the floor slab with a retarder that's placed on the masonry, or you should fill those areas at the floor slab up solidly so that air does not transport through there. Some of the things we've been looking at, polyethylene materials, I mentioned Stego and Raven. Those are what they call virgin polyethylene. They've only been used once. It's not recycled materials. The stuff that we get in the lumber yard or Menards or any other of these discount places is not a really good vapor retarder. It breaks up in some cases, it dries out, it turns to flakes, and does not continue to provide that vapor retardancy. So go with the good stuff. There's other materials that are sprayed on called liquid boot. They're also very good material for doing those kind of things. Look at the permeability of things like your exterior waterproofing on the foundation. Those as well can act as a vapor retarder, but look at what the permeability is. Permeability is essentially how many grains of water per square foot per degree Fahrenheit between the various sides. So consider those things, look at the technical data. So here are some examples of the type of things that we're looking at. If you're running a 6 mil poly or thicker onto the slab, you can see that's that kind of yellow stuff there. Most of the time that ends at the floor slab corners. We want to make sure that that is either sealed down to the footing or to the wall, or if there is a larger area that you're trying to ventilate, runs up the wall and then is sealed at the top where the floor meets the wall systems. You've got to seal that, any of the cracks, gaps between floor drains and the floor slab, all of those type of things need to be sealed. So here's one of the, what they call the greenest buildings in the country. This is using the convection or the stack effect. So with this sort of central atrium area, this PNC building in Pittsburgh is allowing air to be pulled in. It gets ventilated up. The building has been placed where the normally directional winds are coming. So they're using the negative side pressure of the building as air passes over, what we call a Bernoulli effect. To give you some kind of idea, take a strip of paper, tear it into about a 1-inch strip, hold it by your lower lip and blow over the top of it. As you blow over the top of it, that strip of paper will actually rise up towards the airstream that you're blowing. This is what we call the Bernoulli effect. It creates a negative pressure on the downwind side and can help pull that air out of the building as well. So this building, as you can see here, operates without any mechanical system almost half the time. Think of that to compare to other buildings where we keep hearing the fans running about 100% of the time. This is free mechanical systems, free ventilation that you've got going. So here's a typical underground garage. how we design them. You'll see on the left-hand side, you've got air being pulled in by a fan. It could be a makeup air unit, so it's heated or cooled to temper that space. But somehow there's usually a area well, a vent that shows like a little tower or cupola that comes in, blows through the area. Then on the far end, the air is extracted and shot back out. This is one of those systems where carbon dioxide monitor would be present and turn that thing on and off as the carbon monoxide or carbon dioxide is occurring. It can also be on a timer so that you're exchanging so many air changes. And if we look back, you know, it was what, 10 CFM per car is what they were looking for in ASHRAE, I believe. So here, think of the ventilation systems we're talking about here as operating under the floor slab. This is a house. Radon and other vapor mitigation systems are about the same. The air comes up, goes out through the top on a passive system or is ventilated. It's got the same thing. It's got your barrier on the foundation walls. It's got a barrier up the walls on the exterior. It's, you know, this example shows solid poured concrete or a block wall. If it's solid concrete, not much is going to go through that. Probably a good choice if it's waterproofed on the outside. Again, sealing up all those barriers, providing that adequate aggregate so that the air can move through there is a good thing. Just so you understand, another thing about this is underneath these floor slabs, without any ventilation, we end up in the soils with about 100% relative humidity all the time. Doesn't make any difference where it is. When you start pulling air out of it, that humidity level drops considerably, and it's because what's happening is you're replacing it with air from the interior that's finding its way down. So what do we have that causes us problems in our designs, making sure that this 3 Pascal differential between occupied spaces and the underlying soil actually takes place? Well, weather. You've got winds coming in, you've got temperature differentials, those type of things can have an effect. As we showed with that example at Fort Leonard Wood, just a wind on the outside creates a terrible differential movement inside the building. We're looking at, you know, how the effects of fresh air come into the building, mechanical ventilation, insulation systems. Many people think that, gee, if I fill this area with insulation, I put fiberglass in there and all those sort of things, I'm good to go, that this is great. Well, the fiberglass insulation is more like a coffee filter as well. It'll take the dust and the dirt out of the air, but it won't necessarily remove the contaminants that you're looking for. Making sure the connection of the membranes is all intact. Real important, particularly basement level to first floor level or parking level to retail level on some of these things, that the exterior perimeters are sealed up so that you're not pulling air through from the basement around the perimeter. We see this kind of happening all the time because concrete block, brick, cavity wall systems, stud systems that are overlapping, those areas probably need to have been fire stopped anyway, which can aid in stopping that air passage. That's another way to get that done. Future occupants. Well, you're kind of depending upon designing your system to understand what people are going to do once they occupy the building. It's kind of tough to predict that, but take into consideration so that your systems are sort of in place. They're either a static system that you have a vapor retarder that's placed down, it's a passive system that has the vent going through it, or it has an active system. Those can be defeated and unplugged essentially. The other thing is that severe balance between how much air I bring in to make fresh air intake, the cost of the energy, what we're trying to do there, and all of the opposing things that are trying to save energy rather than bringing the air in because they don't want to heat or cool it. Tenant changes, like I said earlier, the pizza ovens, high volume exhausts. We have seen vapor problems occur in exterior walls because of these high flow exhaust fans, ovens, convection, exhausting of different things, particularly even in an industrial setting. That can happen because you've got, if any painting's going on, you've got a large volume of air that's being pulled out through that. So we're kind of getting to the conclusions here. These are some of them that I wanted to point out, and I've actually got questions here, and we've got a couple of pictures that I can show you as well. Many times there's a variety of things that are taking effect on the building, and that changes from season to season. It changes from summer to winter, how much air you bring in, how much you have to condition that. Some of the air that we have coming in, we are filtering it because outside we obviously have pollen and other pollutants present. You want to make sure that if you're bringing air into a building and what you're trying to do is reduce the amount of pollutants coming in that might be out of the slab, don't be putting the intake air next to the loading dock, because what happens is the trucks back up to the loading dock, the guy leaves the diesel truck running, and the fumes from the diesel truck get sucked right in the fresh air intake and cause problems. It's even worse in the wintertime because of the concentration of the diesel. Not all buildings are the same. You're not going to be able to do a one-size-fits-all. If you're placing the building deeper into the area that contains the contaminants you're trying to resist, you got to think further about how you get that membrane to wrap all the way around. And we like to use a theme of what we call holding the pencil to the paper. Essentially, you start at the grade level and you start tracing down the wall without taking the pencil up, wrapping around whatever that object is when you're looking at it in section, under the floor slab, around the footings, up underneath crawl spaces, along the foundation, so that you're creating this impermeable barrier. The engineers need to understand all the different issues that are going on. What are the chemicals that we're dealing with? What are the building systems? When you're designing these mitigation systems, take all those things into account. And I see we have a question that's come up.
Yeah, Steve, just real quick here, a question has come in regarding the cost of a vapor extraction system on a site that once housed an old gas station or dry cleaner. What can someone expect to budget for if that's what they indeed have to do?
That's a good question. Each one of them is a little bit different. If you've got an existing building, trying to get it sealed up is really tough. A mitigation system would be just drilling a hole in, putting it in. You're probably 10 grand or so going up through it. The vapor retarders have been anywhere from 50 cents to $1 a square foot to put them down. It really depends on how big a square footage footprint that you have, but that's just a little bit of a guideline. If you can get in and put an extraction system in that actually has horizontal runs of pipe and aggregate, great. If this is new construction, a lot easier. If it's retrofitting, a lot more difficult, but ultimately the cost will probably be a little less. Okay. Also remember, I think the last point I want to make was that these buildings have the potential to operate outside of the norm. You're going to have cases where things are going to be imbalanced. Equipment wears out, it doesn't get done, has human interference, people turn it off, inadvertently turn it off. Don't think they've done that, but I've seen too many LEED platinum buildings that we've been asked to come in, and you find out that it's often in the computer system that somebody has done something unwittingly and shut off the ventilation, or changed the percentage of fresh air intake, or in one instance totally closed off the fresh air. So I've got time for some questions, or we can talk about how you measure the pollutants underneath a floor slab, which is what we have here. Is a vacuum canister that's used, and the material, air sample is extracted through the floor. That's taken back and analyzed to determine what's in there, what you actually need to try and mitigate. You can place an epoxy on top of some of these floors, so you have a topical vapor retarder, or underneath. I think that's all the pictures I have. Any other questions out there, please type them in.
Well, thank you for attending today's webinar. We will be sending out an email shortly after the presentation with a recording of today's presentation, along with a short survey. Please keep your eyes on your mailbox for future webinars. If more questions come to mind, please email them to Steve Flayton at sflayton@braunintertech.com, and I'll spell that for you. SFLATEN at braunintertech, which is one word, .com, or simply visit our website. I certainly hope you have a fantastic day, and once again, thanks for listening to our webinar.